Alright, this is lecture 5 and today we will have further discussion on chemical equilibrium. One of the topics, one of the points that I mentioned last time is that chemical equilibrium may not always be adequate. So, we discussed something about that in the context of an IC engine example. Remember a spark ignition engine example where the flame is propagating. I said that in the post flame gases, the burnt gases which are behind the flame, they can be thought of as being in equilibrium, at least approximately so. Whereas in the flame zone there are many short lived species, the reaction rates are very fast and the reaction zone is very thin. Usually chemical equilibrium assumption is not very good. So, chemical equilibrium also has its own limitations. We spoke about the limitations of complete combustion situation. So, chemical equilibrium also has limitations. So, that is one point that I would like you to remember from the last class. Then of course, the other point that I mentioned is that if you have a equation on if you see an equation which is like C3H8 plus 5 times air, that is O2 plus 3.76 N2, giving you 3 CO2 plus 4 H2O plus 18.8 N2, that sort of stuff. I told you last time that this is only an atom balance. This is not actually a reaction. This is not a chemical reaction. If somebody tells you this is a chemical reaction, that is not correct. This is an overall representation. This is an overall mass balance. This is just balancing atoms. That is all it is. So, these are two very important things to remember from last class, and let us also recollect what we did with the example. So, there was an example where we have CO2 kept at various pressures and temperatures, and at various pressures and temperatures CO2 had different levels of dissociation. So, we assumed that the equilibrium mixture will have CO2, it will have carbon monoxide, it will have oxygen, and the extent to which CO2 will dissociate will depend on the pressure and temperature that you are talking about. And we had this extensive calculations with the help of 3 equations. We set up 3 equations to calculate the mole fractions of the 3 species, which is CO2, CO and O2. We calculated all those for various pressures and temperatures, and finally we had this plot, and we looked at that plot when we could conclude that the trends that you see in the plot in terms of changing pressure and changing temperature could be interpreted even with the help of Le Chatelier's principle. So, that was last class. Now, we also appreciate the fact that the CO2 example was rather easy. CO2 is just breaking into CO and O2, whereas we are often interested in more combustion type examples where we have, let us say, hydrocarbon burning in air. So, in such cases what do we do? You can still do equilibrium calculations if you want to find out the equilibrium composition, but in the CO2 example we followed an equilibrium constant approach. So, we wrote equilibrium constant, and equilibrium constant could be written in terms of mole fractions of the 3 species. So, that helped us set up one equation. The other 2 equations came from carbon oxygen atom ratio and the sum of mole fractions equal to 1. So, that is how we solved it. This is called an equilibrium constant approach, which of course derives itself from second law, but this is not a very convenient way of doing it. So, it so happens that there are better ways of doing these calculations, and I briefly told you about this in the last class. I said that there is actually an element potential method which uses the method of Lagrange multipliers to minimize Gibbs free energy. Okay. So, at equilibrium dG becomes equal to 0. So, if you do that with the help of this element potential method, which we are really not discussing here in class, but if you do that, then the method becomes easier and solving equations is more systematic and things like that. And there are softwares which do that, there are web based calculators which do that, and I told you in the last class that there is a calculator at Colorado State University. It is also there in the tutorial sheet that I gave you. So, it gives you a web address. So, if you go to that web address and run the calculator, you will be able to calculate the mole fractions and temperatures corresponding to equilibrium. So, that is part of your job when you do those problems which I gave you in the sheet. Now, what I want to do now is to show you some results of calculators like the one at Colorado State website. So, it gives you something like this. Now, what is this for? Let us look at this closely. This is for propane air combustion. This is propane air combustion, pressure 1 atmosphere, temperature is 298 Kelvin. So, this means that the reactants are propane and air, they are at pressure of 1 atmosphere, temperature of 298 Kelvin, and for that reactant condition we are trying to plot the mole fractions of various species. So, what are the species that are plotted here? You can see H2O here, you can see carbon dioxide, this plot is for carbon dioxide, this one is for carbon monoxide, this is hydrogen, this is O2, and this one in dashed line is nitrogen, but nitrogen numbers divided by 10, because nitrogen numbers are higher, as we can understand, because much of air is nitrogen. Apart from these mole fractions, you also have the adiabatic flame temperature plotted. So, this is the adiabatic flame temperature. Now, the mole fractions and the adiabatic flame temperature are plotted as a function of the equivalence ratio. So, you remember what is equivalence ratio? Equivalence ratio is air fuel ratio stoichiometric divided by air fuel ratio actual, and you can vary the equivalence ratio. Let us say you choose 1 mole of fuel, you can change the amount of air that you take, you can change the number of moles of air that you take, and that will give you different equivalence ratios. So, you have to run that calculator on any software that you are using to do these calculations several times. You choose a particular air fuel ratio, that will give you a particular equivalence ratio. So, you choose some point here, and for that point you get a value of O2 mole fraction, CO2 mole fraction, H2O mole fraction, adiabatic flame temperature, and you keep running the software again and again for different equivalence ratios to generate these plots. That is how these have been obtained. Now, what do we learn from here? We learn that the adiabatic flame temperature is maximum for propane air at an equivalence ratio which is slightly richer than stoichiometric. So, if you see here that there is a phi equal to 1.05 at the top. Okay. So, that is 1.05 means this is slightly rich, phi equal to 1 is stoichiometric, phi equal to 1.05 is slightly rich. So, for a slightly rich mixture of propane air, you will get the maximum flame temperature, maximum adiabatic flame temperature. So, if you change the fuel instead of propane, if you take any other hydrocarbon, this trend is usually observed. So, for hydrocarbons it is always slightly rich, for which you get the maximum temperature. And you also see that the adiabatic flame temperature is lower for lean mixtures, and again there is a lower for rich mixtures, because for the theoretically correct mixture, close to the theoretically correct mixture, you get the maximum temperature. Either way you go, whether you go the lean side or the rich side, you are either giving less fuel or you are giving too much fuel, that is less air, then the combustion is not very efficient, and then you get lower temperatures, lower flame temperatures. So, the adiabatic flame temperature has to be read from this scale here. The maximum for propane air is 2278 Kelvin. Let us also remember the fact that this is only for propane air when the reactants are at 1 atmosphere and 298 Kelvin. If you increase the reactant temperature, for example, suppose instead of 298 Kelvin you make it 598 Kelvin, the temperature is going to increase, because the reactants are preheated. So, they are coming in with more enthalpy, and that will give you higher value of temperature. Now, let us look at some of the other profiles. You have H2O, for example. So, this water vapor, and H2O will have, H2O is a product of combustion, one of the products of combustion. So, you will get H2O here for lean mixture. For rich mixture you tend to get somewhat more H2O, and this is CO2 trend like this. Again you have to verify all this by running calculators, and you can also look at O2, carbon monoxide, and hydrogen. So, for lean mixtures you expect to see O2. So, if the mixture is lean, let us say the mixture is 0.8, equivalence ratio of 0.8, you will get significant amount of O2. if the mixture is about stoichiometric, you get much less amount of O2. If the mixture is really rich, then you are not supplying enough air, so you don't expect to see a lot of O2. So the extent of O2 becomes much less. And for rich mixtures, you also get hydrogen and carbon monoxide because they are not getting sufficient oxygen to get oxidized to water vapor or to carbon dioxide. Now, all these species have been obtained for propane air combustion, where propane is at propane air are both at 1 atmosphere, 298 Kelvin. But we do this calculation with respect to certain thermodynamic constraints. So we have to remember that also. So is this uniform? Is this constant internal energy, constant volume? No, not that sort of calculation. This calculation is for constant enthalpy, constant pressure. Okay, so when you do these calculations, second law calculations, you have to give two constraints. So this is constant enthalpy and constant pressure. Okay, so these are, if you see H2O, CO2, CO, O2 and H2 in this plot, these are in significant numbers. They are more than a few percent, sometimes more than 10%. H2 for some of the mixtures are actually more than 15%. Now these are all major species of combustion because they exist in significant quantities. There are also minor products of combustion. The minor products of combustion are like this. So you can see here, these are minor products of combustion. Again, on the y axis you have mole fraction, on the x axis you have equivalence ratio. Let's see what other products can be, combustion products can be seen now. You can now see H atom, for example, which was not there in the previous plot. So these are minor species. You can also see OH. So OH is a radical, so you can see that. You can see NO, so this is nitric oxide, and you can see also O atom. So these are also there, but these are there in smaller numbers. So this mole fraction which you see on the y axis is in the units of parts per million, ppm. So this is no longer percentage. So this is parts per million. And expectedly you see much less oxygen atom on the rich side and more oxygen atom on the lean side. You can also see more H atom on the rich side and less H atom on the lean side, but you see some H atoms, so that means there is some dissociation going on. So it also tells you again, this is again a reminder that complete combustion assumption is not correct and equilibrium is better, in the sense that it takes care of more species. If you assumed complete combustion, you would have been just happy with CO2 and H2O. Okay. Now, so there are some species which is showing up as minor species which were not there as major species, but there are some species which show up in both the plots. Okay. So you see O2 here. O2 was there in the previous plot also. So this O2 is it a minor species or a major species? It is a minor species on the rich side, isn't it? You can see from here that O2 is a minor species for the rich combustion, when the equivalence ratio is more than 1. So this is roughly in that region where equivalence ratio is more than 1, so you tend to get O2. Whereas for lean combustion, it goes through the top of this plot and lands up in the other plot for major species, because the numbers are much higher. In the other plot that we had, the first one, those mole fractions values are in percentages. Here the mole fraction values are in ppm, right? So we'll have to do the following here. You will have to spend some time looking at all these and see whether you can interpret this properly. And we'll try to, in future, we'll also try to do some exercise using calculators to get all these mole fractions ourselves. So we have done CO2 dissociation, and we have also presented results of propane combustion with air, assuming chemical equilibrium. Now, if we wanted to do even the CO2 calculations in class, that would not have been easy, because remember we had 3 equations and one of those was nonlinear. So, doing all these calculations in class was not feasible even for CO2, and for propane air it is pretty much out of question. Okay, could not have done in class, but we can do this as maybe homework problem sometime later. Now, we will have to move to something else. So, we have discussed chemical equilibrium, and now we will have to also talk about chemical kinetics. So, again very quickly, what I said is that to reach equilibrium you need to give sufficient time. Sometimes that time is not there. Okay, sometimes species are not, reactions are not getting enough time to equilibrate. So, what I mentioned last time is this case when you have a mixture spark ignition engine. Remember, the piston is moving, things are changing dynamically, you get this flame, then the flame keeps getting bigger. I said that behind the flame, this part is burnt gas, ahead of the flame, let us use U with blue here, blue to mean cooler, red is hotter, and so this is unburnt mixture and this burnt mixture. So, I said that the burnt mixture has these combustion products which are getting somewhat more time. So, in that time reactions can equilibrate. So, it is a better approximation for the post flame gases, the burnt gases, to be in equilibrium. Whereas in the flame is too thin, there are a lot of short lived species, reaction is happening very fast, there is not enough time. The residence time in the reaction zone which we are calling flame is actually very thin. So, there is not enough time there. So, it is not in equilibrium. So, flame as such is non-equilibrium. So, chemical equilibrium calculations will not work very well. So, what do we want to know about chemical kinetics, and what is it that chemical equilibrium could not tell us? Chemical equilibrium could not tell us that what was the time for completion of reactions, what was the rate of reaction, that chemical equilibrium could not tell us. It was only like this, that if there is sufficient time, what will be the product composition. If there is sufficient time, then what will be the temperature of the products. That is all we could do. Now, again another point which we mentioned last time, that if you have this giving you this, this is not really a reaction, this is an overall representation. So, the actual reaction happens in multiple steps, very large number of steps. So, if it is methane air combustion, maybe more than 200 reactions. So, if you have a hydrocarbon like maybe C3H8 or maybe CH4 or whatever, that is going to break, and the oxidizer also probably is going to break, and the reaction will take place in ways that we right now do not understand. But if you give it sufficient time, maybe it will give you products like CO2, carbon monoxide, oxygen atom, OH radical, and things like that. So, if reactions do not happen this way, then how do reactions happen? Reactions happen in elementary steps. So, the elementary steps can be through maybe unimolecular reaction, so O2 breaking up into O plus O, this is a unimolecular reaction. You can think of other reactions like this, and it can also be bimolecular. So, bimolecular will mean These are some examples. So, this is H. So, H can come from somewhere and there is oxygen available in the system. So, H plus O2 will give you OH plus O. Now, these are called elementary reactions, unimolecular reaction, bimolecular reaction, even termolecular reactions. Termolecular reactions will mean three things reacting with one another. So, these are elementary reactions. Now, these elementary reactions actually do happen, unlike that C3H8 plus 5 times O2 plus 3.76 N2, that business. Now, why is it that C3H8 does not react with 5 times O2 plus 3.76 N2 in one go straight away? It does not happen because if you put, let us say, propane gas and air together, it is extremely unlikely that C3H8 will be hit by 5 O2 molecules at the same time and that will produce carbon dioxide and H2. The probability of that happening is pretty much non-existent. So, that is why it does not happen. Whereas, in a combustion system, there are always at high temperatures there are radicals and then maybe O2 breaking into O plus O, maybe H2 breaking into H plus H, things like that is happening, and that H finds an O2 molecule and then it gives you OH plus O. Maybe there is OH already available, H2 is already available, H2 has come from maybe part of combustion reaction. Okay, so some H2 available. So, that OH reacts with H2 to give you H2 plus H. So, all these reactions are possible, all these reactions, elementary reactions will happen. They have the possibility of happening. So, it is not very difficult because an H atom only has to find an O2 molecule and then they have a collision, then there will be a reaction. Yeah.
These elementary reactions, they are confirmed experimentally, or is it just probabilistic determination?
No, they can be the rates, they can be experimentally confirmed and their rates can also be measured. So, the rates have also been measured. Okay. So, this is not pure hypothesis. So, these reactions do happen, unlike what I was saying, that C3H8 plus 5 times O2 plus 3.76 N2 or stuff like that, those will not happen. So, what we are interested in is knowing something about how to determine rates of reactions, because in a combustion system there is finite time. Okay. Time is an important factor in combustion. Think about that SI engine example, isn't time important? How much time will you get for the expansion stroke in an engine? So, you have these 4 strokes and that will take you how much time? Can you estimate that? Less than a second is fine, but how much? If I tell you the speed of the engine, is it possible to calculate? How will you do that? 4 strokes will take you how many revolutions? 2 revolutions. And if you know the speed of the engine, you know how many revolutions are there per minute. So, you can find out how much time is required for 2 revolutions. Okay. Now, what is the combustion time? Is it the time for 2 revolutions? Does combustion happen for the entire duration of 2 revolutions? No, much less, right? Does it happen consuming the time of 1 full stroke? 1 full stroke? No, even less than that, isn't it? So, during the power stroke, during the expansion stroke, there is combustion taking place, but piston is coming down and you want to complete the combustion as quickly as possible, so that you can produce these hot gases which will push the piston down. So, you want combustion, but you want that combustion to happen quickly, and you can estimate the time depending on the speed of the engine. I told you how to estimate this, at least have a rough estimate. So, the number will be very small. Okay. And you need to know whether the amount of fuel that you are sending for the amount of air that is there in the cylinder, whether the reactions will be fast enough. You have to be able to make some estimate, so that you will know that whether it is realistic to send that much amount of fuel with air. So, time is important. If you have a lot of time, as I said, maybe equilibrium assumption is going to hold. But as we understand now, at least in the flame region, we don't expect the chemical equilibrium assumption to hold. So maybe something else. So chemical kinetics. So we have to estimate rates of reactions. If we can estimate rates of reactions, we will be able to also say how much time the combustion process is going to take. So that's what we want. So we are bothered about rates. Now, to understand rates, we'll do something which is kind of simple in the sense that we'll think about a collision theory of bimolecular reaction. Now, how do reactions happen? One way to think about that is that you have maybe placed two gases. It's easier to think in terms of gases. So A and B are two gases which can react with one another. So you have put them together, and molecules of A and B, they have their own kinetic energies. They're moving about. There's Brownian motion, random motion. So if they both move about, then A will strike B, B will strike A. That will keep happening. So there will be collisions, and these collisions might turn out to be reactive. And if they turn out to be reactive, then from A plus B, you will get C plus D. So examples of this, of course, as I mentioned a few minutes back, is something like this. This can happen, or a few other examples which I already wrote. Now, the collision theory helps us think about rates of reactions in a simple fashion. So there are collisions between A and B, and every time there is a collision, you may not get a reaction. Okay. So if you know something about the velocity distributions of A and B, and if you know the temperature and things like that, going to kinetic theory, you may be able to say something about the rates at which collisions will take place, right? And some of those collisions will turn out to be reactive. All those collisions will not turn out to be reactive, because when the species A and B strike each other, they need sufficient energy. If they are coming and striking each other with sufficient energy, then they may be able to react. So there is a threshold beyond which that reaction will take place. If they have sufficient energy, then reaction will take place, otherwise reaction will not take place. So we are interested in, let's say in this case, as I said, we are interested in rate of reaction. So we are interested in minus d dt of the concentration of A. Now A in square brackets is the concentration of A. So this is kilomole per cubic meter. So what I will write here is that this A is in kilomole per unit volume. So this whole thing is kilomole per meter cube second. A is getting consumed. I have written A plus B giving you C plus D, and this arrow is single headed. Single headed arrow, which means that A and B are irreversibly getting converted to C and D. So as of now, we are not considering C and D again reacting and going back to A plus B. That can be done, but that's like going to an equilibrium discussion again. So I don't want to do that. I'm just trying to think of what happens when A and B are reacting, bimolecular elementary reaction, and what is the rate of consumption of A. That's the question that I'm interested in. So minus dA dt is something we are interested in. Why do we have the minus sign? Yeah, so A is getting consumed. So concentration of A is kilomole per cubic meter. A is getting consumed. From C and D, you are not getting A back. So we know that dA dt is going to be negative. So we put a minus sign in front of it, so that we get minus dA dt, and that's what we are interested in. Yeah. All right. So, this is minus dA dt, and now what I will do is, before I go to an expression which comes from collision theory, I will just write something and ask you to possibly interpret this. So, I write minus dA dt here, which is this, which is a multiplication of 3 things. Okay. A lot of text here. All right. So, the 3 things in bracket, maybe we can even give them some names if you want. We can call them, this is 1, this is 2, this is 3. All right. So, we have this kinetic theory, and then we know something about velocity distributions. We are bringing in collision theory. So, we will be able to estimate these things, and then finally, whatever we have written in brackets can be written in terms of things which we more readily recognize. For example, we can bring in temperature, we can bring in concentrations, we can also bring in molecular dimensions, we can bring in Avogadro's number, things like that. So, but that is in the next stage. Okay. But here we are trying to just ascertain, I have just written these, and you can look at this and tell me whether 1 into 2 into 3 is really minus dA dt. Is it minus dA dt? 1 into 2 into 3. Okay. Now, what is 1 into 2? What is 1 into 2? If you look at
collisions that are that gives the reaction.
Yes, so that is a very good answer. See, 1 is just number of collisions per unit volume per unit time. If you multiply it by the probability that a collision leads to reaction, then you get the number of reactive collisions, collisions in which A and B will in fact react with one another and give you C plus D. So, that is the number of reactive collisions per unit volume per unit time, because per unit volume per unit time is already there in 1. That is 1 into 2 is number of reactive collisions per unit volume per unit time. Okay. Now, if you multiply 1 into 2 with 3, what do you get? Do you get minus dA dt? That is the question. So, let us think about this. We got the number of reactive collisions per unit volume per unit time, but ultimately how will that translate to the kilomoles of A per unit volume per unit time? All right. So, let us remember this, that A plus B is giving you C plus D. What happens to number of molecules of A in every reactive collision? What is the relation between the number of reactive collisions and the number of molecules of A lost? Same in the sense that every time you have a reactive collision, you lose one molecule of A. All right. So, 1 into 2 is number of reactive collisions per unit volume per unit time, or it can also be the number of molecules of A which are lost per unit volume per unit time. Okay. So, that is 1 into 2. As I said, think of 1 into 2 multiplied by 3. So, you will get now a fraction which is number of molecules of A which are consumed in reaction divided by number of molecules of A, total number of molecules of A. So, you get a fraction which tells you the number of molecules, fraction of number of molecules of A which are getting consumed by reaction, okay, multiplied by, we left out this term, kilomole of A. So, that fraction multiplied by kilomoles of A will give you the kilomoles of A which are getting consumed because of reaction, but do not forget per unit volume per unit time, that was there in the first term. So, that all is happening per unit volume per unit time. So, this should match minus dA dt, correct. Very quickly, 1 into 2 number of molecules of A lost because of reaction per unit volume per unit time. Okay. Split 3 into 2 parts. Think first about the denominator which has number of molecules of A, total number of molecules of A. 1 into 2 gave you the number of molecules of A which are getting lost. That divided by this denominator will give you the fraction of molecules of A which are getting consumed. Okay. What was left? Kilomole of A. We have to bring him in because we can't bring him, cannot send him out. So, that fraction multiplied by kilomoles of A is the kilomoles of A which are getting consumed. Okay. Per unit volume per unit time. Per unit volume will make that kilomole into kilomole per cubic meter, or per unit time will of course give you the rate. So, this is consistent, fine. Now, we are going to leave out a lot of stuff. I am just going to write you the expression, write here the expression for minus dA dt based on collision theory. So, again I am skipping, but remember that we can't do everything in a combustion course because I have to borrow stuff from other books and other subjects, can't do everything in detail. So, here is what it is. You can get this expression in Stephen Turns' book also. So, this is A, and we actually write this as K into A into B. All right. So, this is a complicated thing, but again we just borrowed it from somewhere. All we need to do is to just see what these terms are and if possible interpret this. So, minus dA dt is this, no doubt, because this comes from experimental observations, and I am sure you have seen this in chemistry sometime or the other. Reaction rates in terms of a reaction rate constant into concentrations of the reactants. This is something which you probably have not seen. So, this I have just taken from the book. This is coming from collision theory. So, what are these? NAV is Avogadro's number, sigma AB is sigma A plus sigma B by 2, where sigma A and sigma B are hard sphere diameters. Sigma A and sigma B are hard sphere diameters of species A and B. Now, species A, if you think about the structure, it is not hard sphere, but you also know, probably if you think about physics, we sometimes assume them to be like billiard balls. Okay. So, those are like hard spheres. So, that kind of equivalent diameter is sigma A and sigma B. So, average of sigma A and sigma B is sigma AB. So, we will use that. So, this number can easily come, this number can come from data books and physics books and whatever. Avogadro's number is NAV here, which we already know. Now, this KB is Boltzmann constant. Okay. So, again you know what that is from physics. Mu is a quantity Ma plus Mb. So, for example, if you want to know m of, let us say, H2, m of H2. So, then what you do is, okay, in what is the mass of 6.022 into 10 to the power 23 number of H2s? That is 2.008 grams. Okay, this many number of molecules giving you 2 grams roughly. So, that 2 divided by 6.022 into 10 to the power 23 will give you the mass of H2, things like that. So, this is also obtainable. So, we get mu. Okay. Coming back to this, I told you this is Avogadro's number. I told you what sigma AB is. This is Boltzmann constant. This of course is temperature. I just now told you mu, and I did not tell you about R bar, but you know R bar. This is universal gas constant. What is E? I did not tell you, but I think you know. Activation energy. So, reactions have activation energy, and if you have A and B colliding with one another, then they have to have sufficient energy to cross what we call an activation energy barrier to be able to give you a reactive collision. So, you have A and B striking each other, there is a collision, they should have sufficient energy to in fact overcome the activation energy barrier and give you a reactive collision which will bring forth C and D. That is the idea. Okay. So, I have basically told you everything. Now, A and B here, this A and B here is expected, because we know that the reaction rates, from whatever little chemistry you may have studied, you know that the reaction rates are going to depend on the concentrations. So, reaction rate will depend on concentration of A, concentration of B, right. So, what is new that we have learned today? We already from chemistry we knew that minus dA dt is K into A into B. So, you knew that these are reaction rate, the rate of consumption of A is dependent on concentration of A and concentration of B. Okay. So, this was known. What is extra that we have learned today? We have learned that of course, it has a reaction rate is a temperature dependence. So, you knew that to some extent, now you know that better, because now you see that there are two terms through which the temperature dependence of minus dA dt comes. So, one term is of course exponential minus E over R bar T. Okay. So, this tells you that reaction rates are temperature dependent, and you have this another term here which has got temperature to the power half. So, this gives you another temperature dependence. Of course, it is very easy to see that when talking about temperature dependence, this must be a stronger temperature dependence, whereas this is only T to the power half. So, this is a weak dependence, this is an exponential dependence, this is a very strong dependence. So, we will look into this little later. It tells you that the reaction rate depends on sizes of molecules and masses of molecules and things like that. That I think is expected. There is one term which I did not tell you about, that is this P here, this term here. This is called a steric factor. So, STERIC, or a geometric factor, steric factor or geometric factor. So, when collisions happen, reactions will result if the reactant molecules are carrying enough energy with them to be able to cross the activation energy barrier and then give you a reaction product. That is correct, but apart from that there is a geometrical factor also. So, if you have for example H and OH, you have H and OH, we kind of intuitively expect that if H goes and strikes the O side of the OH radical, then a reaction is more likely. If it goes on this side, probably it is less possible. So, the factor P takes care of this kind of geometrical issues. So, this is another number which one can pick up. So, p is a geometrical factor or a steric factor. This number p is actually less than 1. All right. Now, based on whatever we have studied so far about reaction rates, we can also see that if we plot, let us say, all right. So, this minus dA dt is k times A into B, and for k we have that this lengthy expression which we saw. We have the expression for k from collision theory. So, this is not something which we obtained experimentally. So, it may not be accurate, but this gives you some idea of dependencies. Now, if you do experiments, you can verify that log of k goes with 1 over t, and you get data points like this, and you also get data points like this, telling you that you can actually get 2 sets of lines depending on the temperature range that you are talking about. So, this you can verify experimentally. So, what do? You have A and B, you let them react. You have some ways of measuring concentration of A as a function of time and also concentration of B. So, from that you can figure out the reaction rate constant K. So, this is something which chemists have done for centuries. So, this is standard measurement. So, from that you can get K. So, you can get log of K, and you can plot that as a function of 1 over T. All the data will not fall in one straight line, but you can identify regimes in which you get one straight line and another regime which you got another straight line. So, this is for what sort of temperature? Higher temperature. So, higher temperature means smaller 1 over T. Higher temperature means smaller 1 over T. So, you are in this region. So, you get this straight line. At lower temperature you get another set of straight line. So, the person who in fact came up with this sort of experiment and this sort of ideas was, of course, you know who that was? Arrhenius. Okay, that was Arrhenius. So, if looking at this plot, log of k versus 1 over t, you can say that this will happen. Right. So, log of k with 1 over t giving you a straight line will mean that k as a function of temperature is some A times exponential minus E over R bar T. So, A is here a pre-exponential factor. E again is activation energy. So, this is experimentally verifiable. So, this is what can be written. In fact, sometimes it is better to write so this is one option, this is another option. So, why two things here? Any idea?
A may be temperature dependent.
Yeah, so A has a temperature dependence, and we have some idea of this, because remember that we had this term 8 pi kb temperature whole thing to the power half. So, temperature dependence of reaction rate comes through that exponential factor, but also in a factor preceding that, that had the t to the power half. So, to take care of that, you can use the t to the power b, not half, because that half was from theory. In reality, it may not be half, but it may still be a small number. Okay. So, there is a power dependence on temperature, a weak power dependence on temperature, but also an exponential dependence on temperature. Fine. So, I think we have done enough today. With just one quick calculation we would like to do. If you have a calculator, then we will try to just quickly check something. So, how important is this factor exponential minus E over R bar T? Now, we will check this. Now, let us consider an elementary reaction which is OH plus O. H plus O2 giving you OH plus O, and for this one the activation energy is 69.1 kilojoule per mole. Okay. So, if that is the case, then let us calculate this term at 300 Kelvin. So, at 300 Kelvin it will be e to the power minus 69.1 into 10 cube divided by this, and let us also calculate at maybe 310 Kelvin or so. So, it is the same thing with this 300 replaced by 310. So, can somebody quickly tell me what this is, what this number is? If you have a calculator, I will need help on this. I am not carrying a calculator. 9.32. 9.3 into 10 to the power minus 13. Yeah, quite possible. At least it seems to be all right. Now, at 310 K. Two point 2.27 10 to the power minus 12. Okay. So, what is the ratio of the two then? This is of course bigger. So, what is the ratio? 2.27 10 to the power minus 12 is at 310 Kelvin. If we divide that by 9.3 into 10 to the power minus 13, I am assuming that Karthik's calculations are correct.
Yes.
Okay. So, what is this ratio? 2.43. Good. So, what does that tell you? It tells you that if you just increase the temperature by 10 Kelvin, the reaction rate almost goes up by a factor of 2.5. So, this tells you that reaction rates, because of their exponential dependence on temperature, are highly temperature sensitive. So, if you have a hydrocarbon vapor with air, and if there is a hot spot somewhere, then because of that rise in temperature, reaction rate will start picking up. Near that hot spot, that mixture will start getting heated up and it will pick up, the reaction rate will pick up. And as its temperature, as the reaction picks up, it releases heat, that will raise the temperature further, and that way reaction rate will keep on increasing because it is so sensitive to temperature, and finally it will catch fire. Okay. So, this exponential of minus E by R bar T is also called an energy factor. It is called an energy factor, and this is something which is very important for us. When you are trying to initiate a reaction, then you try to give a spark, or maybe you try to bring a small flame in the mixture. What you are trying to do is locally raise the temperature so that the reaction starts proceeding further, so that things become fast. Okay. So, I think we are running out of time, and we will stop here today. What we will try to do in the next class is actually explore this energy factor a little bit, and also talk about activation energy, and then go to maybe some analysis of other kinds of reactions. We just looked at bimolecular reactions, we will look at other kinds of reactions, and we will have to slowly start looking at situations when there is not just one reaction, there are multiple reactions. Remember that if we write H plus O2 giving you OH plus O, that is an elementary reaction, that is a good thing because that actually happens. C3H8 plus 5 times all that business, that does not really happen, isn't it? So, when we are looking at elementary reactions, we are trying to understand something, but just understanding one elementary reaction is not going to help. If you have multiple elementary reactions happening, and which is the case, hundreds of reactions, multiple reactions happening together, then how does one affect the other and things like that. So our focus will also be to go in that direction in the next few classes. All right, thank you.